Lie down, close your eyes, and allow the world around you to soften into silence. Let your breathing settle into a slow, measured rhythm, and imagine the earth as it once was, long before the moon first appeared to hang in the sky. Picture a world without lunar light, without tides pulled gently across oceans, a young planet spinning alone in the vast emptiness of space. What was Earth like in that time, when it had not yet been touched by the presence of a companion so familiar to us now? Billions of years ago, the solar system was a turbulent place, a cloud of gas and dust stirred by gravity and scattered by collisions. From this nebular material, the sun ignited, and around it, planets began to coalesce. In this early era, approximately 4.6 billion years ago, tiny particles of rock, ice, and metal collided and merged repeatedly, forming larger and larger bodies called planetesimals. Among them, proto-Earth grew steadily, drawing in material through gravity while fending off violent impacts that could shatter or reshape it entirely. Early Earth was not yet the blue and green world we know today. Its surface was dominated by molten rock, a searing landscape of liquid magma oceans that glowed with the deep reds and oranges of extreme heat. Heavy elements sank toward the center, forming a dense metallic core, while lighter silicate minerals floated above, gradually creating layers that would become the mantle and crust. The planet's rotation was rapid, spinning once in perhaps only 6 hours, and its days were shorter and nights briefer than what would later become familiar. The primordial atmosphere was thin and volatile, formed largely from gases released during outgassing of the planet's interior. Carbon dioxide, nitrogen, water vapor, and traces of hydrogen and other compounds swirled over the molten surface, forming clouds that trapped heat and contributed to a greenhouse effect far stronger than that of the modern Earth. Without the stabilizing influence of a moon, the planet's axial tilt fluctuated more wildly, altering seasonal intensity and creating a chaotic interplay of light and shadow over the young land masses. Frequent bombardment by remaining planetesimals and larger protoplanets left the surface scarred, molten pools constantly reforming as impacts struck the Earth. Each collision delivered energy that melted portions of the crust and atmosphere, occasionally vaporizing oceans that had begun to condense from cooling steam. Minerals fused into new forms, and the chemical composition of the surface shifted continuously as the planet matured. Water, though present in trace amounts, began to accumulate as the Earth cooled. Outgassed water vapor condensed and fell as torrential rains onto the glowing rock below. Early oceans may have been acidic and heavy with dissolved minerals, but they provided the first stable reservoirs of liquid on the planet's surface. The absence of a moon meant there were no tides in the way we understand them. The shallow waves and localized movements of water were dictated instead by wind, density differences, and occasional asteroid impacts, creating a world where water's rhythm was irregular and unpredictable. Volcanism dominated the landscape. Vast shield volcanoes, explosive stratovolcanoes, and fissures in the crust poured molten rock into the surroundings, forming new crust and releasing additional gases into the atmosphere. The constant outpouring of sulfur, carbon dioxide, and nitrogen shaped the chemical environment of the early atmosphere, creating a thick, hazy sky that filtered sunlight in diffuse shades of amber and crimson. Lightning storms surged through these clouds, providing electrical energy that would become important for chemical reactions in the oceans below. The planet's rapid rotation influenced atmospheric dynamics, generating high-speed winds and powerful storms that swept across continents yet to stabilize. The axial wobble was irregular, producing long-term variations in climate intensity. Without a moon's gravitational pull to stabilize its tilt, Earth's orientation in space shifted gradually, causing periodic extremes in solar exposure at different latitudes. These variations contributed to the uneven heating of the surface, affecting evaporation, condensation, and the nascent cycle of precipitation. Beneath the surface, the molten iron core generated the planet's first magnetic field. This geomagnetic shield protected the early atmosphere from being stripped away by solar winds and cosmic radiation. The field also influenced charged particles in the upper atmosphere, forming a primitive version of auroral displays, flickering with energy as the planet rotated. The combination of magnetic protection and a thick, dense atmosphere allowed the accumulation of water and other volatiles critical for the development of a stable environment. In the oceans and shallow pools, simple chemical reactions were taking place. Organic molecules, formed from the interaction of volcanic gases, water, and energy sources such as lightning or ultraviolet radiation, began to accumulate. These molecules, while not yet life, created a chemical richness that would later serve as the foundation for prebiotic chemistry. The absence of tidal cycles meant these molecules were distributed by currents, rainfall, and evaporation patterns alone, leading to isolated pockets of concentrated compounds in which early reactions could take place. Comparing this Earth to neighboring planets highlights its unique qualities. Venus, with its thick, crushing atmosphere, and Mars, with its thin, frigid envelope, offered contrasts that underscore Earth's relative suitability for retaining liquid water and nurturing complex chemistry. The combination of mass, distance from the Sun, early volcanism, and protective magnetic field created conditions not perfectly hospitable, but capable of supporting chemical evolution in ways no other nearby world could match at that time. Throughout these billions of years, cosmic events continued to shape the young planet. Comets and asteroids delivered water, carbon, and other essential elements, supplementing those already present. Impacts not only altered the surface, but also delivered kinetic energy that promoted chemical mixing. Earth, still alone in its orbit, evolved steadily in response to these forces, a dynamic and changing world waiting for the stabilizing companion that would later become the Moon. In this silent epoch, Earth's days passed rapidly, filled with glowing horizons, volcanic plumes, and the hiss of early oceans. The planet's surface was constantly renewing itself through cycles of melting, cooling, and impact. In the sky above, stars shone with a clarity unbroken by lunar reflection, and the young sun cast its unfiltered light across a world both violent and full of latent potential. Without the moon, the rhythms of this Earth were irregular but profoundly formative, setting the stage for the emergence of an environment capable of sustaining life in the eons to follow. As Earth cooled further, the crust began to stabilize in places, forming the first rudimentary continents. These were not the familiar land masses of today, but irregular, shifting plates of solid rock floating atop a molten mantle. Their edges were jagged and unstable, prone to fracturing and sinking under repeated stresses from tectonic movements. These early plates collided, tore apart, and fused together in a slow dance dictated by the heat of the underlying mantle and the convective currents driving their motion. The molten interior constantly pushed and pulled the crust, creating regions of uplift and subsidence that shaped the primitive landscape. Volcanic activity remained intense along these early boundaries. Basaltic lava flows spread across low-lying areas, filling depressions and contributing to the growth of continents, while explosive eruptions blasted ash and gases high into the dense atmosphere. The interaction of magma with accumulating water created violent, steam-driven explosions, forming calderas and pumice deposits that would eventually erode and blend into new layers of the forming crust. These events released vast amounts of carbon dioxide, sulfur compounds, and nitrogen, reinforcing the greenhouse conditions that kept the planet's surface warm despite its young sun emitting less energy than it does today. The early oceans, still forming from condensed water vapor, were deep pools of chemically active liquid. They contained dissolved minerals leached from newly formed rocks, including magnesium, calcium, and various salts, creating the first semblances of seawater. These oceans experienced irregular movement, stirred by wind, density differences, and the occasional asteroid impact. Without a moon to induce tidal patterns, the distribution of water across shallow basins was uneven, producing isolated regions where concentrations of organic molecules could gather. These pools became natural laboratories for chemical reactions that synthesized increasingly complex compounds, essential precursors to life. Lightning storms, frequent and intense within the thick, turbulent atmosphere, injected energy into these oceans. Electric discharges could break molecular bonds in water and atmospheric gases, creating reactive radicals and simple organic compounds. Simultaneously, volcanic vents on the ocean floor emitted mineral-rich fluids heated by Earth's interior. These hydrothermal systems provided chemical gradients and stable environments in which reactions could proceed over long periods. The interplay of energy, minerals, and water created pockets where chemical complexity could increase, setting the groundwork for prebiotic evolution long before life emerged. Earth's rotation continued to influence these early processes. Rapid spinning created pronounced Coriolis effects, shaping atmospheric circulation and ocean currents. The faster rotation generated stronger equatorial winds and intense storm systems, while polar regions experienced less turbulent flows. Seasonal variations were unpredictable, subject to the shifting axial tilt, producing periods of relative calm interspersed with extreme heating or cooling. These fluctuating conditions influenced evaporation rates, condensation, and nutrient cycling within the oceans, further contributing to the concentration of organic compounds in select locations. Beneath the surface, differentiation of the interior continued. The heavy iron-nickel core solidified gradually at its center, while the surrounding molten outer core maintained convective motion that sustained Earth's magnetic field. This magnetic field protected the nascent atmosphere from erosion by the solar wind, preserving volatile compounds such as water and carbon dioxide. Without such protection, the thin layers of gases surrounding Earth could have been stripped away, leaving a barren world similar to what Venus or Mars experienced. In this way, the magnetic field was not only a shield, but a stabilizing force, maintaining the conditions necessary for chemical evolution on the surface. Meteorite impacts continued, bringing both destructive and constructive effects. Large collisions could melt vast regions of the crust and inject energy into the atmosphere and oceans. But they also delivered additional water, carbon-based molecules, and trace metals. Each impact redistributed material across the planet, contributing to chemical mixing and the formation of localized environments that could concentrate specific elements or compounds. These sporadic events, while violent, were instrumental in shaping the chemical diversity of early Earth's oceans and crust. The chemical environment in the oceans was dynamic. Salts, minerals, and organic compounds dissolved and precipitated, forming gradients and microenvironments ideal for prebiotic reactions. Shallow pools evaporated under solar heat, concentrating solutes, while deeper basins provided stable conditions shielded from surface temperature fluctuations. The combination of concentrated reactants, energy inputs from lightning and geothermal activity, and mineral surfaces that could act as catalysts allowed increasingly complex molecules such as amino acids and simple nucleotides to form and persist. These compounds remained transient but increasingly abundant, creating a chemical richness unique to this time in Earth's history. Atmospheric chemistry evolved in tandem with surface processes. Carbon dioxide and nitrogen dominated, while trace gases such as methane, ammonia, and hydrogen contributed to chemical reactivity. Ultraviolet radiation from the young sun penetrated the thin atmosphere, breaking molecular bonds and driving photochemical reactions. The resulting products accumulated in the oceans and on exposed rock surfaces, creating diverse chemical reservoirs. Without a moon to regulate Earth's rotation or stabilize its tilt, variations in sunlight exposure across latitudes created localized zones of differing energy input, further diversifying the chemical landscape. Early Earth's surface temperature was moderated not only by greenhouse gases, but also by the interplay of volcanic activity and ocean coverage. The presence of liquid water allowed partial heat absorption and redistribution across the globe, while volcanic aerosols in the atmosphere reflected sunlight and provided transient cooling. This dynamic balance produced a planet neither uniformly hot nor entirely cooled, but in a constant state of flux that allowed chemical systems to develop complexity. Each cycle of heating and cooling, each rainfall and evaporation event, and each collision of molten rock and water contributed incrementally to the planet's evolving chemical and physical state. Over long periods, tectonic movements slowly rearranged continental fragments. Crustal recycling exposed new mineral surfaces to atmospheric and oceanic interactions, replenishing essential elements and nutrients. Hydrothermal systems shifted with plate movements, creating new chemical niches and replenishing previously exhausted resources. In these ways, Earth maintained a dynamic yet stable platform for prebiotic chemistry, steadily building the foundation for future biological activity. Even in the absence of the moon, these geological and chemical processes unfolded in a delicate balance that allowed the planet to mature while remaining volatile and active. Above it all, the sky remained thick with volcanic haze and early clouds. Sunlight filtered in diffused amber and orange tones, occasionally breaking through to illuminate molten plains and simmering oceans. The absence of the moon left the night sky dominated by distant stars, unsoftened by lunar glow, a stark contrast to the rhythmic illumination familiar to later epochs. These long, unlit nights and rapidly spinning days affected evaporation, wind patterns, and the thermal cycling of water, creating conditions unlike those experienced on any subsequent Earth. Even without a lunar companion, Earth developed a remarkable combination of forces: rotation, volcanic activity, magnetic protection, chemical diversity, and nascent oceans that set the stage for the emergence of life. Each component interacted subtly but persistently with the others. The molten interior drove surface reshaping and magnetic protection. The volatile atmosphere enabled chemical reactions and moderated temperatures. Water collected in basins and pools, carrying dissolved minerals and organic compounds. Together, these processes formed a coherent, functioning system on a young planet, spinning alone. A world in which the absence of a moon did not prevent complexity, but instead allowed processes to unfold in their rawest, most direct forms. Over millions of years, the shallow oceans and basins of early Earth became increasingly complex chemical laboratories. Evaporation in isolated pools concentrated salts and organic molecules, while intermittent rains diluted and redistributed compounds, producing gradients critical for chemical interactions. The mineral surfaces of rocks provided scaffolding for reactions, allowing amino acids, simple sugars, and nucleotides to accumulate in localized pockets. Hydrothermal vents on the seafloor offered another stable environment, rich in dissolved metals and minerals, creating chemical gradients that persisted even as surface conditions fluctuated. These regions acted as incubators of molecular complexity, where reactions could proceed over extended periods without disruption. Thermal energy from volcanic activity and heat retained within the oceans drove convection currents, moving molecules through temperature gradients. Such gradients encouraged the formation of increasingly complex molecules and may have promoted the assembly of primitive polymers. Ultraviolet radiation from the sun, penetrating the thin atmosphere, further energized chemical reactions, splitting simple molecules and allowing radicals to recombine into more complex structures. This interplay of energy sources and chemical substrates created a diverse chemical ecosystem, a dynamic network of reactive compounds circulating through the oceans and across mineral surfaces. The composition of the early atmosphere influenced the chemistry of these oceans. Carbon dioxide, a major component, dissolved readily in water, forming carbonic acid that interacted with minerals to produce carbonate deposits. Nitrogen, largely inert, provided a stable background, while methane, ammonia, and hydrogen contributed to chemical reactivity. Sulfur compounds from volcanic emissions introduced additional pathways for chemical synthesis, particularly in hydrothermal environments. The balance of these gases, though transient and subject to constant replenishment or loss, defined the chemical environment in which complex molecules could emerge. Without a moon, Earth's rotation remained rapid, creating short, intense days and nights. The fast spin generated stronger equatorial winds and larger storm systems, which in turn stirred the oceans, redistributing chemical compounds. The lack of tidal influence meant that the concentration of solutes in shallow pools relied primarily on localized evaporation, rainfall, and occasional impact events. This created heterogeneity in chemical environments, with some regions becoming rich in certain compounds, while others remained relatively unreactive. Such diversity may have been advantageous, offering multiple chemical experiments occurring simultaneously across the planet. Meteorite impacts continue to play a subtle role. Small to moderate collisions not only delivered additional water and organic molecules, but also provided localized energy inputs. The heat generated by these impacts temporarily melted sections of crust and ocean, creating hotspots where chemical reactions could proceed more rapidly. Large impacts could vaporize regions entirely, redistributing compounds and occasionally sterilizing surfaces, but they also mixed materials across the globe, maintaining chemical heterogeneity necessary for prebiotic processes. In deeper ocean basins, hydrothermal circulation sustained gradients of temperature, pH, and chemical composition. These gradients provided long-term stability for chemical evolution, in contrast to the more variable surface pools. Minerals such as iron, nickel, and magnesium from vent emissions acted as catalysts, facilitating reactions that might not occur spontaneously in solution. The combination of thermal and chemical gradients, catalysis by minerals, and continuous flow of fluids created conditions ideal for the assembly of increasingly complex organic molecules. Volcanic eruptions shaped both the chemical and physical landscape. Ash and fine particles ejected into the atmosphere settled over oceans and land, providing services for adsorption and catalysis. Sulfur dioxide and other gases dissolved in rainwater, altering ocean chemistry and contributing to acidity that influenced mineral solubility. Over time, these processes added layers of chemical complexity to early Earth's surface, enriching the oceans with a variety of reactive species that would become essential building blocks for life. Even as the planet's surface remained dynamic, there was a gradual trend toward stabilization. Continental fragments, though small and shifting, provided localized relief from constant volcanism and impact resurfacing. These emerging highlands created sheltered pools and lagoons where chemical concentrations could persist longer than in open ocean environments. Such areas may have acted as crucibles for sustained prebiotic chemistry, allowing longer reaction times and the accumulation of increasingly complex molecules. Earth's magnetic field continued to shield the atmosphere and surface from the harmful solar radiation. Without this protection, volatile compounds and dissolved molecules in surface waters might have been stripped away or broken down too rapidly for chemical complexity to develop. The magnetic field, coupled with a dense early atmosphere, preserved these critical materials and allowed them to interact in a relatively controlled chemical environment, despite the otherwise chaotic conditions of the young planet. Atmospheric circulation patterns, driven by rapid rotation and uneven heating, further contributed to chemical distribution. Winds transported aerosols and soluble gases across the planet, depositing them in isolated basins or shallow pools. Rainfall acted as both a solvent and a transporter, carrying dissolved compounds from volcanic regions or higher terrain into ocean basins and lowlands. This continuous mixing maintained chemical diversity and replenished local concentrations necessary for prebiotic synthesis. As Earth's surface and atmosphere evolved, a subtle balance began to emerge between destructive and constructive forces. Meteorite impacts, volcanic activity, and solar radiation continuously disrupted localized chemical systems, yet they also provided energy, redistributed materials, and introduced new compounds. Water circulated through pools, oceans, and hydrothermal vents, allowing repeated reactions and gradual accumulation of molecular complexity. Even without a moon, Earth's chemical environment became increasingly structured, developing zones where prebiotic processes could proceed consistently over millions of years. The interplay of geology, chemistry, and environmental dynamics created a planet uniquely prepared for the eventual emergence of life. Every volcanic eruption, every rainfall, every minor impact contributed incrementally to chemical evolution. Earth's oceans, though influenced by wind rather than lunar tides, displayed a dynamic interplay of mixing, concentration, and chemical stratification. Mineral surfaces, hydrothermal gradients, and atmospheric inputs combined to create a network of reactive environments capable of supporting the formation of complex organic molecules. The absence of a moon did not prevent progress. It allowed Earth's processes to unfold in their raw, uninterrupted state, a laboratory of natural chemistry spanning the entire surface. As the eons passed, Earth's climate began to show subtle patterns, even without the stabilizing presence of a moon. The rapid rotation produced short, intense days that alternated with equally brief nights, creating sharp temperature fluctuations across the surface. Equatorial regions experienced strong heating, driving evaporation from shallow pools and oceans, while polar regions, though less extreme than modern Antarctica, remained cooler and subject to intermittent condensation. These temperature differences generated winds that circulated across the planet, stirring oceans and redistributing chemical compounds from one region to another. Axial tilt, unconstrained by a lunar companion, varied irregularly over long timescales. Without a moon to stabilize Earth's orientation, tilt changes amplified seasonal contrasts, causing periods of stronger heating at high latitudes and extreme cooling in other areas. Such variability affected the distribution of water in the atmosphere, rainfall patterns, and evaporation rates. In shallow pools, these fluctuations led to cycles of concentration and dilution, fostering microenvironments where organic molecules could gather, interact, and transform. Chemical niches were transient but repeated, giving compounds multiple opportunities to combine into more complex structures. The oceans themselves were in constant motion, stirred by wind, density differences, and occasional impact events. Shallow basins experienced episodic drying, followed by rapid refilling during heavy rains, concentrating dissolved salts and organic compounds. Deeper basins provided relative stability, where minerals and molecules could persist and accumulate over extended periods. Hydrothermal vent systems on the seafloor continued to deliver heat, metals, and sulfur compounds, maintaining localized chemical gradients. These gradients were essential for catalyzing reactions that could produce increasingly complex molecular assemblies, including polymers necessary for future biochemical processes. Volcanic activity remained a dominant influence on climate and chemistry. Plumes of ash and sulfur compounds ejected into the atmosphere altered the spectral quality of sunlight, producing diffuse light that warmed certain regions while cooling others. Acidic rain, formed from sulfur dioxide and other volcanic gases, fell on both oceans and land, interacting with minerals and releasing nutrients into the water. This continual exchange between atmosphere, lithosphere, and hydrosphere established a dynamic, interdependent system in which chemical complexity could flourish despite ongoing disruption. Meteorite impacts continued to shape localized environments. Small collisions delivered additional water, carbon, and nitrogen compounds, while also creating thermal energy that temporarily altered local chemical conditions. Large impacts were less frequent, but highly influential, remelting crust and vaporizing portions of the ocean, redistributing both heat and compounds. Each collision contributed to the chemical diversity of early Earth, ensuring that no single region remained chemically stagnant for long. This constant mixing, though destructive in places, was vital to maintaining the dynamic equilibrium necessary for prebiotic chemistry. Lightning storms in the dense, hazy atmosphere provided bursts of energy capable of breaking molecular bonds, producing reactive radicals. Combined with ultraviolet radiation from the young sun, these energy sources drove the formation of new organic molecules, continually replenishing the chemical inventory of the oceans. Organic molecules, such as amino acids, simple sugars, and nucleotides, accumulated preferentially in pools and basins, where evaporation and chemical concentration occurred. These pockets of enriched chemistry were scattered across the planet, forming a mosaic of potential prebiotic laboratories. The interplay of rotation, atmospheric circulation, and chemical distribution created irregular but repeating cycles across Earth's surface. Wind-driven currents transported solids from one basin to another, while rainfall and evaporation generated concentration gradients necessary for complex reactions. Hydrothermal systems provided stable, long-lasting gradients in deeper regions, allowing reactions that might otherwise be disrupted at the surface to proceed uninterrupted. Together, these processes maintain chemical diversity at both micro and macro scales, creating numerous pathways for the gradual assembly of complex molecules. Minerals present on the ocean floor and in shallow pools played a critical catalytic role. Surfaces of clays and metal-rich substrates facilitated chemical reactions by stabilizing intermediates and concentrating reactants. Iron, nickel, magnesium, and other transition metals from both hydrothermal vents and weathered rocks enhanced reaction rates and created sites for molecular assembly. Over millions of years, this consistent availability of catalytic surfaces allowed the gradual buildup of increasingly intricate organic molecules, setting the stage for the eventual emergence of self-replicating chemical systems. Even in the absence of lunar tides, water movement and distribution maintained sufficient variability to create microenvironments conducive to prebiotic evolution. Pools concentrated by evaporation, basins enriched by rainfall, and currents moving dissolved compounds across the ocean created the diversity of chemical conditions necessary for the synthesis of complex molecules. Each of these localized environments represented a separate experiment in chemical evolution, allowing multiple reaction pathways to be explored simultaneously across the surface of early Earth. Earth's magnetic field, generated by the convecting molten outer core, continued to provide essential protection for these developing chemical systems. By deflecting high-energy particles from the young sun, the field preserved volatile compounds in the atmosphere and shielded surface molecules from destructive radiation. This protection allowed organic compounds to persist long enough for increasingly complex reactions to occur. In combination with volcanic, hydrothermal, and atmospheric energy sources, this geomagnetic protection helped maintain a stable platform for ongoing chemical evolution. Through all of these processes, rotation, volcanism, meteorite impacts, atmospheric chemistry, oceanic circulation, and magnetic shielding, Earth developed a uniquely dynamic and chemically rich environment. The absence of a moon did not inhibit these processes. Rather, it allowed them to operate in raw, natural form. The young planet evolved under its own intrinsic forces, creating a vast array of chemical landscapes where molecules could interact, combine, and persist, gradually laying the foundation for the emergence of life. Beneath the oceans, thermal layering began to establish subtle patterns of stability. Dense, mineral-rich waters near hydrothermal vents sank toward the deep basins, while warmer, less saline waters remained near the surface. These gradients produced zones of differing temperature, chemical composition, and energy availability, allowing distinct chemical processes to occur simultaneously within the same ocean. In shallow areas, repeated cycles of evaporation and replenishment from rainfall created isolated pools with concentrated solutes, while deeper regions retained dissolved compounds over extended periods, protected from rapid surface fluctuations. Such stratification created a natural diversity of chemical microenvironments, each capable of supporting the gradual assembly of increasingly complex organic molecules. The primitive crust itself continued to evolve through both internal and external processes. Convection within the mantle generated slow movements of crustal fragments, causing collisions, rifting, and subduction in various regions. These tectonic processes exposed fresh minerals to the oceans, continuously replenishing catalytic surfaces necessary for chemical reactions. Volcanic activity, particularly along mid-ocean ridges and rift zones, delivered heat and additional chemical compounds into the oceans, reinforcing gradients and providing localized energy inputs that sustained chemical evolution over long timescales. In regions where volcanic islands emerged, interactions between molten rock and shallow pools of water produced intense, localized chemical activity. Steam-driven explosions mixed minerals, dissolved gases, and organic compounds in highly reactive environments. As the molten rock cooled and solidified, it provided surfaces for adsorption and catalysis, facilitating chemical reactions that might not have occurred in solution alone. These processes contributed incrementally to the increasing complexity of organic molecules in both shallow and deeper regions. Meteorite impacts, though sporadic, continued to influence ocean chemistry and distribution. Each collision delivered water, carbon, nitrogen, and trace metals, supplementing compounds already present. Larger impacts created transient heat zones, vaporizing portions of oceans and altering chemical distributions, while smaller impacts provided localized disturbances that redistributed solutes across shallow basins. Together, these events maintained heterogeneity in chemical environments, ensuring that no region remained chemically stagnant for long periods. Atmospheric circulation interacted with surface waters to further diversify chemical conditions. Rapid winds transported dissolved gases, aerosols, and fine volcanic particles across continents and oceans, depositing them in localized basins and shallow pools. Rainfall redistributed soluble compounds, while evaporation concentrated them, creating cyclical patterns of enrichment and dilution. These repeated cycles allowed certain compounds to accumulate in higher concentrations, enhancing opportunities for chemical reactions that could produce increasingly complex molecules. Lightning and ultraviolet radiation remained significant energy sources driving chemical synthesis. Electrical discharges broke bonds in simple molecules, producing reactive radicals that recombined into more complex species. ultraviolet radiation facilitated photochemical reactions in surface waters and thin films on mineral surfaces, creating compounds that could not form under thermal or aqueous conditions alone. These energy sources, in combination with the chemical richness of the oceans and mineral surfaces, created a multiplicity of reaction pathways, each contributing to the gradual buildup of prebiotic complexity. Even without lunar tides, localized water movements generated sufficient variability to maintain chemical gradients. Evaporation, rainfall, wind-driven currents, and hydrothermal circulation provided continual redistribution of solutes, ensuring that reactive compounds encountered each other repeatedly. Concentrated pools acted as natural laboratories, while deeper basins offered stability for ongoing reactions. This duality of dynamic and stable environments allowed molecules to persist, interact, and increasingly assemble into larger structures, laying the groundwork for polymerization and prebiotic chemical networks. Minerals played a critical catalytic role throughout this process. Clays, iron-rich substrates, and magnesium silicates provided surfaces where molecules could align, bind, and react more efficiently. Transition metals delivered by volcanic eruptions and meteorite impacts facilitated electron transfer reactions essential for assembling larger, more complex molecules. Over millions of years, these mineral-mediated reactions contributed to the incremental formation of macromolecules, including polymers capable of storing information and catalyzing further reactions. The young planet's rapid rotation continued to influence these processes. Strong equatorial winds and storm systems enhanced mixing in the oceans, while day-night cycles affected surface temperature and evaporation patterns. Axial tilt variations created longer-term cycles of heating and cooling across latitudes, producing intermittent changes in chemical concentration and distribution. These dynamic conditions, though less regular than modern tidal cycles, provided a rich variety of chemical environments in which prebiotic reactions could proceed simultaneously on a planetary scale. Throughout this period, Earth's magnetic field preserved volatile compounds by deflecting high-energy solar particles. This protection maintained the integrity of dissolved and surface-bound molecules, allowing them to persist long enough for complex reactions to occur. In combination with hydrothermal gradients, atmospheric energy inputs, and mineral surfaces, the magnetic field helps sustain the chemical diversity necessary for prebiotic evolution. The planet, though still alone in its orbit, possessed all the internal and external mechanisms to foster complexity, demonstrating that life's foundational chemistry could progress even without a lunar companion. The interplay of these forces, hydrothermal circulation, atmospheric dynamics, chemical gradients, mineral catalysis, energy inputs, and repeated redistribution, produced a coherent system of chemical evolution. Pools, oceans, and vent systems acted as interlinked environments, each contributing to the gradual assembly of increasingly complex molecules. Over time, these processes formed a dynamic network of prebiotic chemistry, a planetary laboratory in which molecular complexity could build steadily, shaping Earth into a world primed for life despite the absence of the moon. As chemical complexity increased in the oceans and shallow pools, interactions between dissolved molecules and mineral surfaces became more intricate. Clays and metal-rich substrates provided not only scaffolding for reactions, but also microenvironments with slightly different pH levels, ionic strengths, and thermal conditions. These subtle variations created pockets where particular reactions were favored, allowing certain molecules to accumulate more efficiently than in surrounding waters. Over thousands of years, these localized chemical niches became increasingly sophisticated, each contributing uniquely to the overall network of prebiotic chemistry. Hydrothermal vents remained especially critical to these processes. Superheated fluids, rich in minerals such as iron, nickel, and magnesium, mixed with cooler seawater to create sharp chemical gradients. Within these gradients, molecules could assemble, react, and sometimes form primitive polymers. The combination of temperature difference, mineral catalysis, and continuous fluid flow allowed certain molecules to persist longer than they would in the more dynamic surface waters, creating conditions in which incremental chemical evolution could occur. These vent systems, isolated yet continuously fed by Earth's internal heat, were stable chemical laboratories operating in parallel with the more variable shallow pools. Surface chemistry was equally dynamic. Shallow water basins experienced repeated cycles of concentration and dilution due to evaporation and rainfall, producing chemical gradients across small distances. Ultraviolet radiation provided energy for photochemical reactions at the water-air interface, while lightning strikes initiated radical-driven synthesis. The interaction of these energy sources with concentrated solutes created opportunities for molecules to form bonds that were otherwise energetically unfavorable in dilute conditions. This constant flux encouraged diversification of molecular types, with some molecules persisting longer, others breaking down, and new ones forming in an ongoing chemical dialogue. Meteorite impacts, though unpredictable, supplied both raw materials and energy inputs. Organic compounds, water, and trace metals delivered from space augmented the existing chemical inventory, while the energy released by impacts created localized heat zones where reactions could accelerate. Repeated impacts redistributed molecules across the oceans, mixing previously isolated chemical pools and enabling novel reactions. These events, while disruptive, were crucial in preventing chemical stagnation, allowing multiple reaction pathways to operate simultaneously across Earth's surface. Tectonic activity contributed additional variation. The movement of crustal fragments exposed new minerals to the oceans, replenishing catalytic surfaces necessary for ongoing chemical synthesis. Volcanic eruptions released gases and particulates into the atmosphere, some of which dissolved into surface waters, altering pH and providing additional reactants. The interplay of these processes, hydrothermal vent chemistry, surface pool dynamics, meteorite contributions, and tectonic resurfacing, maintained a rich and continuously evolving chemical environment, capable of supporting increasingly complex molecular assemblies. The oceans themselves exhibited internal gradients that influence molecular stability. Warmer surface waters mixed with cooler, denser waters below, creating zones where temperature-sensitive reactions could proceed at optimal rates. Salinity differences produced density gradients that affected molecule mobility, allowing certain compounds to concentrate in specific layers. These stratifications, though subtle, provided stability within a generally dynamic environment, ensuring that molecules could persist long enough to participate in sequential reactions, gradually assembling into larger, more complex structures. Lightning and ultraviolet radiation remained key drivers of chemical evolution at the surface. Electrical discharges in the dense, volatile atmosphere initiated radical formation, breaking molecular bonds and allowing recombination into more complex structures. Ultraviolet photons drove photochemical transformations that could produce compounds otherwise unattainable under thermal or aqueous conditions. Together, these energy sources supplemented the chemical diversity generated by geological processes, reinforcing the development of a robust prebiotic inventory. Mineral surfaces continued to serve as critical facilitators of chemical synthesis. Transition metals adsorbed onto clays and silicate surfaces provided sites for electron transfer, enabling the formation of covalent bonds between reactive species. These surfaces also protected fragile molecules from degradation by shielding them from radiation and thermal fluctuations, creating microenvironments where incremental molecular assembly could occur over extended periods. Over millennia, such catalytic sites contributed significantly to the accumulation of increasingly complex organic polymers. Even in the absence of tidal modulation by a moon, water movement provided sufficient variation to maintain dynamic chemical networks. Currents, wind-driven circulation, and localized rainfall and evaporation cycles redistributed compounds across the surface and shallow basins, ensuring repeated encounters between reactive molecules. Hydrothermal gradients and stratified deep waters provided complementary stable environments, allowing reactions that required persistent conditions to progress uninterrupted. This combination of variability and stability across Earth's oceans created an extensive chemical landscape capable of sustaining progressive molecular complexity. As a result, Earth became a planet of interlinked chemical microenvironments, each operating under slightly different conditions but collectively contributing to the global network of prebiotic chemistry. Shallow pools, deep basins, hydrothermal vents, mineral surfaces, and atmospheric interactions work together, producing increasingly intricate molecules and polymers over millions of years. Despite the absence of the moon, these processes unfolded in parallel, shaping a chemically diverse, dynamic planet that steadily approached the threshold of life's earliest molecular precursors. Over time, simple organic molecules began to interact in increasingly complex ways. Amino acids formed in shallow pools could bind together under favorable conditions, producing short chains, or peptides, that were more stable than individual molecules. Nucleotides, synthesized from combinations of simpler precursors, delivered both through atmospheric reactions and hydrothermal processes, occasionally linked into short sequences. These early polymers were fragile, often breaking apart under heat or chemical fluctuations, but persistent cycles of concentration, dilution, and energy input allowed new assemblies to form repeatedly, gradually increasing the diversity and complexity of molecular structures. In deeper hydrothermal systems, the combination of thermal gradients, mineral surfaces, and continuous flow created stable reaction environments. Molecules could adsorb onto metallic or clay surfaces, orienting in ways that promoted bond formation. Over millennia, these environments allowed certain sequences of reactions to occur repeatedly, giving rise to molecules that were increasingly resilient and capable of self-propagating chemical interactions. The vent systems acted as chemical incubators, complementing the transient but diverse reactions occurring in surface pools. Shallow basins remained critical as chemical laboratories exposed to sunlight and atmospheric inputs. Ultraviolet light drove photochemical transformations, while lightning and heat from the sun facilitated energy-intensive reactions. Evaporation cycles concentrated solutes, increasing the likelihood that reactive molecules encountered one another. Rainfall replenished these pools, allowing cycles of dissolution and reconcentration to continue over thousands of years. In this way, shallow pools provided intermittent but potent bursts of chemical evolution, contrasting with the stable, gradual processes occurring in hydrothermal environments. Meteorite impacts continued to influence chemical networks by delivering fresh material and locally energizing reactions. Organic molecules, water, and trace metals from space were incorporated into existing chemical systems, while impact heat temporarily accelerated reactions and redistributed molecules across shallow basins and deeper ocean layers. These infrequent but powerful events prevented chemical stagnation and ensured the global network of reactions remained dynamic, allowing novel molecular interactions to occur across widely separated regions. The tectonic evolution of the crust contributed to the ongoing diversification of chemical environments. Subduction zones recycled minerals, while rifting and volcanic activity exposed new catalytic surfaces. Basaltic rocks weathered into clay-rich sediments, providing additional sites for adsorption and catalysis. Mineral diversity in these environments allowed a wide range of reactions to proceed simultaneously, with different regions favoring distinct molecular pathways. Over geological timescales, this heterogeneity was essential for producing a broad array of prebiotic molecules, increasing the likelihood that life's precursors could emerge. Salinity gradients in shallow pools and along oceanic margins created additional chemical niches. Water movement redistributed salts and dissolved compounds, concentrating certain elements in localized areas. These gradients affected molecular interactions, influencing the stability and reactivity of early polymers. By creating microenvironments with subtly different conditions, Earth's oceans allowed multiple reaction pathways to proceed concurrently, fostering diversity and redundancy in chemical evolution. Even without tidal forces, these natural gradients ensured dynamic yet structured chemical landscapes. Atmospheric gases continued to interact with surface waters, delivering reactive species and influencing chemical pathways. Carbon dioxide dissolved in water, forming weak acids that facilitated mineral interactions and catalysis. Nitrogen, methane, ammonia, and hydrogen participated in reactions driven by ultraviolet light and electrical discharges. Sulfur compounds from volcanic emissions further diversified reaction pathways, creating alternative routes for molecular assembly. The combination of atmospheric inputs and surface chemistry produced a complex web of reactions, each contributing incrementally to the formation of increasingly sophisticated organic structures. Mineral surfaces served as scaffolds for molecular assembly. Clays, silicates, and metal oxides adsorbed molecules, stabilizing reactive intermediates and promoting the formation of longer chains. Transition metals, particularly iron, nickel, and magnesium, facilitated electron transfer, enabling reactions that would otherwise be energetically unfavorable. Over long periods, repeated adsorption and desorption cycles allowed polymers to grow, fragment, and reassemble, gradually increasing chemical complexity across the planet's surface and oceans. The dynamic interplay of energy sources, chemical diversity, and environmental variation created conditions for the emergence of self-sustaining reaction cycles. Molecules that could persist through evaporation, thermal fluctuation, and chemical disruption began to dominate localized pools and hydrothermal niches. These cycles did not yet constitute life, but they represented a critical step toward proto-biological systems in which chemical networks could maintain continuity, propagate reactions, and gradually increase in complexity over geological timescales. Even without the Moon, Earth's rotation, axial tilt variations, and dynamic surface processes provided sufficient environmental diversity to support these developing networks. Shallow pools, deep hydrothermal systems, atmospheric interactions, mineral surfaces, and periodic energy inputs worked in concert to sustain chemical evolution. The planet's prebiotic environment became a complex, interconnected system in which molecules could combine, reorganize, and accumulate, steadily building the foundation for life's earliest precursors. Over extensive timescales, the network of prebiotic chemistry became increasingly intricate. Molecules that formed in isolated pools occasionally found themselves redistributed into new environments by rainfall, wind, or shallow ocean currents. These transfers allowed different chemical systems to interact, merging previously separate pathways and enabling the formation of more complex molecular assemblies. The combination of stability in some niches and variability in others created a natural laboratory in which diverse reaction networks could persist and adapt to changing conditions. Hydrothermal vents continued to serve as centers of chemical innovation. Steady flows of mineral-rich fluids maintained gradients in temperature, pH, and chemical composition, providing consistent environments for molecular interactions. Molecules adsorbed onto vent surfaces were protected from sudden fluctuations and could participate in sequential reactions that gradually built complexity. Over millennia, these vents allowed the assembly of longer chains of amino acids and nucleotides, laying the groundwork for polymers capable of storing information and catalyzing additional reactions. Shallow pools offered a complementary setting, where intermittent concentration through evaporation and replenishment through rainfall allowed periodic bursts of chemical synthesis. Photochemical reactions driven by ultraviolet light and energy from electrical discharges created molecules not readily formed in deep-sea environments. These pools acted as testing grounds, where a wide variety of molecular combinations could form, break down, and recombine, producing a rich diversity of organic compounds. The repeated cycles of concentration and dilution increased the likelihood that certain sequences would persist long enough to engage in further reactions. Meteorite impacts, though unpredictable, continued to influence chemical evolution. Each impact delivered additional water, organic compounds, and trace metals, enriching the existing inventory of reactants. Thermal energy from impacts accelerated local reactions, while shock waves and ejecta redistributed molecules across nearby pools and ocean regions. These sporadic events, though disruptive, maintained chemical diversity and prevented stagnation, ensuring that multiple reaction pathways continued to operate simultaneously across the planet's surface and oceans. Tectonic movements contributed to the ongoing evolution of prebiotic systems. Shifting crustal plates exposed fresh minerals to interacting waters, replenishing catalytic surfaces and providing new sites for molecular assembly. Volcanic eruptions released gases and particulate matter that dissolved in surface waters, altering pH, ionic strength, and available reactants. The interplay between geological activity, chemical gradients, and environmental variability created a resilient system in which prebiotic reactions could persist, adapt, and accumulate over extended periods. Salinity, temperature, and chemical gradients within oceans and shallow pools created microenvironments that favored different reactions. Variations in solute concentration, dissolved metals, and mineral surfaces allowed distinct molecular networks to emerge independently yet remain interconnected. Some molecules thrived in stable deep water zones, while others persisted in dynamic shallow pools exposed to ultraviolet light and fluctuating conditions. This diversity enhanced the overall robustness of prebiotic chemistry, increasing the probability that functional, self-propagating chemical systems would eventually arise. Minerals remained crucial in mediating chemical reactions. Clay surfaces, silicate frameworks, and transition metals facilitated adsorption, alignment, and electron transfer, enabling reactions that were otherwise energetically unfavorable. Molecules bound to these surfaces were shielded from degradation, allowing incremental assembly of longer chains and more complex structures. Over millions of years, repeated cycles of adsorption, reaction, and desorption contributed to the gradual accumulation of increasingly sophisticated polymers. Energy inputs from sunlight, lightning, and geothermal heat acted synergistically with chemical gradients and mineral catalysis. Ultraviolet light drove photochemical synthesis at the water surface, while lightning initiated radical reactions that transformed simple compounds into more complex molecules. Geothermal heat from vents maintained thermal gradients that supported sequential chemical reactions. Together, these energy sources sustained continuous chemical evolution, enhancing molecular diversity and enabling increasingly complex assemblies to persist across various environments. The interaction between dynamic surface processes and stable hydrothermal systems created a planetary network of chemical microenvironments. Molecules could migrate between pools, vents, and ocean basins, encountering new reactants and conditions that promoted novel reactions. This constant redistribution prevented stagnation, allowing molecular assemblies to evolve incrementally. Over millions of years, these interlinked environments fostered the gradual emergence of protobiological systems, in which molecules not only formed, but also began to interact in self-sustaining networks. Even in the absence of the Moon, Earth's rotation, axial tilt variations, and energy fluxes provided sufficient environmental diversity to drive complex chemical evolution. Day-night cycles, rapid spinning, and atmospheric circulation ensured continual mixing and exposure to energy inputs. Hydrothermal vents offered stable environments for gradual molecular assembly, while surface pools provided bursts of chemical innovation. Combined, these processes created a dynamic yet structured chemical landscape, steadily increasing molecular complexity and setting the stage for the earliest forms of life to emerge. Within the intricate chemical landscape of early Earth, certain molecules began to exhibit behaviors that enhanced their persistence. Polymers formed from amino acids and nucleotides occasionally folded or associated with mineral surfaces in ways that increased stability. protecting them from hydrolysis and radiation. These associations were not life, but they created quasi-stable molecular systems that could persist long enough to participate in further reactions. Over time, the accumulation of such resilient molecules increased the overall chemical complexity of the environment, allowing new reaction pathways to emerge. Hydrothermal vents supplied a continuous source of reduced metals and sulfide ions, which facilitated redox reactions, critical for polymer growth. Molecules adsorbed onto vent surfaces could undergo sequential reactions in a spatially constrained environment, where reactive intermediates were retained long enough to form longer chains. This process allowed some polymers to reach lengths sufficient for rudimentary functional interactions, creating networks of molecules capable of influencing subsequent reactions. These localized molecular networks acted as precursors to metabolic cycles, demonstrating a stepwise progression from simple reactions to interdependent chemical systems. In shallow pools, repeated cycles of concentration and dilution promoted selective stabilization of molecules. Compounds that were resilient under evaporation and UV exposure persisted, while less stable species degraded, creating a natural form of chemical selection. This process enriched pools in molecules capable of repeated interactions, increasing the likelihood of assembling more complex structures. Occasional replenishment by rainfall introduced new reactants, maintaining chemical diversity and allowing continuous experimentation across the planetary surface. The interplay between deep-sea and surface chemistries produced complementary effects. Hydrothermal vents offered stability and continuous energy input, supporting gradual polymerization and network formation. Surface pools provided variable conditions, energy pulses from sunlight and lightning, and opportunities for recombination among diverse molecules. The exchange of compounds between these environments enabled interactions that would not occur in isolation, increasing the overall chemical connectivity and diversity on a planetary scale. Mineral surfaces remained essential in promoting molecular organization. Fine-grained clays, iron-rich silicates, and other mineral substrates offered adsorption sites that oriented molecules for more efficient bond formation. Surface-bound molecules could undergo repeated cycles of reaction without diffusing into bulk solution, allowing sequential chemical steps to accumulate over extended periods. Transition metals in these minerals facilitated electron transfer reactions, promoting polymer elongation and cross-linking that contributed to the formation of complex networks. Meteorite impacts, while sporadic, occasionally introduced novel compounds and energetic conditions that accelerated chemical innovation. Organic molecules, water, and trace elements from extraterrestrial sources supplemented existing systems, while impact heat temporarily enhanced reaction rates in localized regions. This periodic injection of material and energy prevented chemical uniformity, ensuring that diverse reaction pathways continued to operate across the planet and enabling the emergence of molecular assemblies with greater complexity and stability. Salinity gradients, thermal layers, and localized pH differences provided additional structural heterogeneity. Molecules concentrated in high salinity pools or along thermal boundaries experienced selective stabilization, while others remained mobile and reactive in less constrained zones. This natural partitioning allowed multiple chemical systems to coexist, each exploring distinct reaction pathways. The coexistence of stable and dynamic environments created a planetary network of interconnected chemical niches, each contributing uniquely to overall molecular evolution. Energy sources continued to drive reactions without forming life. Lightning, ultraviolet light, and geothermal heat supplied the energy needed to break bonds, form radicals, and drive endergonic reactions. These energy inputs, combined with the chemical and physical heterogeneity of the environment, produced conditions under which molecules could assemble, reorganize, and interact in increasingly intricate networks. Over geological timescales, these processes led to the gradual emergence of chemical systems that were self-sustaining in localized contexts, the precursors to metabolism and replication. Interactions among molecular networks fostered the first feedback cycles. Molecules that stabilized others, catalyzed reactions, or concentrated reactants began to create conditions favorable for their own persistence and for the formation of new molecular assemblies. These feedback loops did not constitute life, but represented a step toward interdependent chemical systems capable of sustaining complexity over time. Networks within hydrothermal vents, shallow pools, and mineral surfaces interacted through migration of molecules, reinforcing connectivity across multiple chemical environments. By integrating stability, energy input, molecular diversity, and feedback processes, early Earth developed a robust system of prebiotic chemistry. Even without the Moon's tidal influence, dynamic cycles of concentration, mixing, and redistribution ensured that chemical networks remained active, diverse, and evolving. The planet was now a mosaic of interacting chemical laboratories, each contributing incrementally to the emergence of self-sustaining molecular systems and steadily advancing toward the threshold of life. As molecular networks became more intricate, the spatial arrangement of reactions gained increasing significance. In hydrothermal vent channels, gradients in temperature and chemical composition produced zones where certain reactions occurred preferentially. Molecules that diffused along these channels encountered complementary reactants in predictable sequences, allowing chain reactions to persist over time. These spatially constrained environments encourage the formation of proto-metabolic cycles in which the products of one reaction could feed subsequent reactions, creating localized loops of chemical activity that enhanced stability and complexity. Shallow pools provided additional opportunities for selective organization, as solute concentrations fluctuated with evaporation and replenishment. Molecules capable of forming transient aggregates persisted longer than isolated compounds. These aggregates acted as scaffolds for further chemical interactions, promoting bond formation and molecular cross-linking. Over extended periods, some aggregates became particularly robust, resisting breakdown and serving as focal points for the assembly of increasingly complex networks of interacting molecules. Chemical compartmentalization emerged naturally through these processes. Differences in solute concentration, pH, salinity, and mineral composition across microenvironments created boundaries within which reactions were effectively isolated from the surrounding milieu. Within these compartments, molecules could undergo multiple reaction cycles without dilution or disruption, allowing the stepwise accumulation of polymers and other complex structures. The presence of many such compartments across the planet enabled parallel chemical evolution, accelerating the overall progression of molecular complexity. Interactions between compartments further expanded chemical diversity. Molecules occasionally transferred from one microenvironment to another, either through surface runoff, diffusion, or convection in shallow waters. When transferred molecules encountered new reactants, novel reactions occurred, generating previously unattainable compounds. These exchanges maintained connectivity across chemical niches, ensuring that no single compartment evolved in isolation, while still allowing localized networks to develop stability and complexity over time. The early crust contributed to the structuring of these chemical environments. Volcanic islands and emerging continental fragments produced topographical variation, influencing water flow, sediment deposition, and mineral exposure. These features created natural conduits and barriers, further subdividing chemical landscapes. Pools trapped between rocky outcrops experienced repeated cycles of concentration, while streams carried dissolved compounds to new locations. This interaction of geology and chemistry shaped diverse reaction environments, each contributing uniquely to molecular evolution. Hydrothermal systems continued to provide high-energy, chemically rich conditions for sequential reactions. Molecules adsorbed to vent surfaces could participate in multiple reactions along the flow path, with products from one site entering subsequent reaction zones. The combination of thermal gradients, mineral catalysis, and continuous supply of reactants facilitated increasingly complex assemblies, some of which exhibited primitive catalytic properties that enhanced the efficiency of subsequent reactions. These systems exemplified the emergence of interdependent chemical networks capable of sustaining themselves over extended periods. Energy pulses at the surface maintained chemical innovation in parallel with vent systems. Lightning discharges initiated radical reactions in surface waters, while ultraviolet light continued to drive photochemical transformations. Evaporation cycles concentrated reactive molecules in shallow pools, allowing interactions that might not occur in bulk solution. These surface-driven processes complemented the slow, continuous reactions in deep water systems, creating a multi-tiered network of chemical evolution operating across spatial scales. The integration of these diverse environments produced emergent chemical properties. Molecules, capable of forming longer chains or stabilizing others, began to dominate certain microenvironments, creating localized centers of complexity. These centers could influence nearby pools or vent systems through migration of molecules, introducing new interactions and fostering additional polymerization. Over long timescales, the cumulative effect was a progressive increase in molecular connectivity, complexity, and functional potential across the planet. Natural feedback mechanisms began to stabilize certain chemical pathways. Molecules that facilitated reactions, concentrated reactants, or protected other compounds became central nodes within reaction networks. While not living systems, these networks displayed resilience, persisting through environmental fluctuations and repeated cycles of disturbance. The presence of multiple interacting networks increased redundancy and robustness, allowing chemical evolution to continue even when individual pathways were disrupted by meteorite impacts, volcanic eruptions, or changes in temperature and salinity. By integrating compartmentalization, spatial organization, energy-driven synthesis, and feedback loops, early Earth established the foundation for prebiotic systems that were increasingly self-reinforcing. Molecules interacted in structured yet dynamic ways, forming proto-metabolic cycles and networks capable of sustaining complexity over geological timescales. Even without a moon, the planet's rotation, axial tilt variations, and diverse surface and subsurface environments provided the necessary scaffolding for the emergence of organized chemical systems, steadily advancing toward the threshold of life. As prebiotic chemical networks matured, selective persistence began to shape molecular assemblies. Polymers that resisted breakdown under repeated cycles of heating, cooling, concentration, and dilution gradually accumulated in certain compartments. Molecules capable of stabilizing others or facilitating sequential reactions became increasingly central to these local systems. Over time, these persistent molecules created scaffolds that supported the formation of larger, more complex networks, effectively concentrating chemical activity in areas where reactions could proceed with greater efficiency. Hydrothermal channels continued to act as conduits for chemical progression. Molecules transported along these flows repeatedly encountered complementary reactants, allowing chain reactions to propagate over distances. In some cases, sequential reactions produced polymers that enhanced the likelihood of further bond formation, creating proto-catalytic behavior. Though rudimentary, these emergent properties exemplified the transition from random chemical interactions to organized networks capable of maintaining continuity over extended periods. Surface pools added bursts of chemical diversity. Evaporation cycles concentrated solutes, while rainfall replenished reactive compounds, creating repeated opportunities for molecular interaction. Ultraviolet light and electrical discharges induced reactions that generated molecules unattainable in deep water systems. Molecules stabilized by aggregation or mineral adsorption persisted through these cycles, allowing iterative reactions to occur over long intervals. These pools functioned as experimental spaces, testing combinations of molecules and gradually favoring assemblies that could endure environmental fluctuations. The exchange of molecules between different compartments reinforced network interconnectivity. Surface waters carrying concentrated molecules could merge with hydrothermal flows, introducing new reactants into stable vent environments. Conversely, deep-water polymers occasionally migrated to shallow basins, exposing them to variable conditions that promoted further chemical innovation. This continuous exchange maintained global connectivity among chemical networks, preventing isolation and allowing diverse molecular strategies to coexist and evolve. Mineral surfaces continued to provide structural support for complex assemblies. Fine-grained clays, silicates, and metal oxides adsorbed polymers, positioning them to participate in subsequent reactions. Transition metals facilitated electron transfer and bond formation, while surfaces offered protection from degradation. Repeated cycles of adsorption, reaction, and desorption promoted the incremental growth of longer polymers and enhanced the functional diversity of molecular networks, gradually increasing their organizational complexity. Energy fluxes sustained chemical evolution without introducing life. Lightning, ultraviolet light, and geothermal heat supplied sufficient energy to break and reform bonds, initiate radical reactions, and drive thermodynamically challenging processes. By providing periodic energy pulses, These sources allowed molecules to explore new configurations, favoring assemblies that could withstand fluctuations and contribute to interconnected reaction networks. Over millions of years, such energy-driven processes steadily increased the resilience and sophistication of molecular systems. Feedback mechanisms emerged within networks, enhancing chemical continuity. Molecules that stabilized or catalyzed reactions increased the persistence of other compounds, creating localized loops of interaction. These feedback loops allowed certain pathways to dominate, while less stable reactions faded, producing a form of chemical selection. Although not biological, these systems demonstrated the potential for self-reinforcing molecular organization, where network structure directly influenced the likelihood of reaction success and compound persistence. Geological features continued to shape chemical evolution. Emerging islands, volcanic slopes, and continental fragments created heterogeneous environments, partitioning pools and streams and concentrating chemical activity. Flowing waters carried reactive molecules between isolated compartments, promoting interactions that would not occur in stagnant systems. The combination of natural compartmentalization, energy input, and material transport ensured that chemical networks remained diverse, connected, and capable of increasing complexity over geological timescales. Through these integrated processes, selective persistence, compartmentalization, energy-driven synthesis, molecular transport, and feedback loops, Earth's prebiotic systems gradually approached a threshold of organization. Molecules were no longer merely reacting independently. They were part of interconnected networks capable of sustaining complexity, propagating reactions, and adapting to environmental fluctuations. The stage was now set for the final incremental steps toward proto-biological systems that could eventually give rise to life as we understand it. Proto-metabolic cycles began to dominate certain microenvironments, particularly in hydrothermal channels and mineral-rich pools. Molecules that facilitated sequential reactions maintained the flow of chemical activity, effectively linking one reaction to another in a self-reinforcing pattern. These cycles did not constitute life, but they displayed continuity. The products of one reaction increased the likelihood of subsequent reactions, establishing rudimentary networks of chemical interdependence. Over long periods, such cycles became increasingly complex, integrating multiple types of polymers and small molecules into coherent systems capable of sustaining themselves locally. Surface-driven chemical systems complemented these cycles. Concentration through evaporation, repeated influx of reactive molecules from rainfall, and energy from ultraviolet light and lightning created high-turnover environments where diverse molecular assemblies formed, interacted, and occasionally persisted. Molecules stabilized by adsorption or aggregation could survive long enough to participate in multiple reaction cycles, linking surface chemistry with subsurface networks. This interplay produced layers of chemical organization where transient innovations from variable environments were reinforced by stable vent-driven processes. The transport of molecules between different environments continued to shape global chemical connectivity. Streams, runoff, and diffusion carried compounds from shallow basins to deeper channels, allowing interactions between networks that had evolved independently. Molecules from hydrothermal systems occasionally reached surface pools, encountering variable conditions that fostered novel reactions. This movement ensured that chemical innovations were not confined, promoting a cumulative increase in molecular complexity and diversity across the planet. Mineral scaffolding enhanced the stability and functionality of these networks. Clays and silicates provided adsorption sites that oriented molecules for bond formation, while metal ions facilitated electron transfer and catalytic reactions. Polymers bound to these surfaces were protected from degradation and could participate in repeated reaction cycles, gradually forming larger and more interconnected assemblies. Over geological timescales, mineral-mediated reactions enabled the emergence of protosystems capable of maintaining continuity and increasing molecular complexity independently of environmental disturbances. Energy inputs remained critical for sustaining these emergent networks. Lightning discharges generated reactive radicals, ultraviolet light drove photochemical synthesis, and geothermal heat maintained thermal gradients that promoted sequential reactions. These energy fluxes allowed molecules to explore new configurations, favoring the accumulation of assemblies capable of withstanding environmental stresses. The combination of continuous energy input, molecular transport, and mineral-mediated stabilization created resilient chemical systems, steadily advancing toward the threshold of proto-biological organization. Feedback mechanisms intensified within these systems. Molecules that catalyzed reactions or stabilized other compounds increased the persistence of their networks, while less stable reactions gradually diminished. This form of chemical selection enriched certain pathways and structures, promoting greater organizational coherence. Over time, networks exhibiting enhanced stability and functional connectivity became more dominant, illustrating the principle of emergent self-maintenance within purely chemical systems. Geological heterogeneity amplified these effects. Rising volcanic islands, spreading ridges, and evolving continental fragments shaped the distribution of chemical environments, partitioning reaction zones, and concentrating molecules in favorable locations. The interaction between geological features and chemical processes produced diverse microenvironments, each with distinct energy fluxes, mineral composition, and solute concentration. This environmental diversity allowed multiple molecular strategies to develop in parallel, increasing the overall resilience and adaptability of prebiotic networks. Cumulative chemical evolution reached a level where localized systems exhibited coordination and sustained activity. Molecules were organized into interdependent networks with energy-driven cycles, feedback loops, and compartmentalization, allowing chemical reactions to proceed continuously. These protosystems demonstrated properties essential for life: persistence, connectivity, and the ability to influence subsequent reactions. Earth's surface and subsurface had now become a planetary laboratory in which prebiotic chemistry had matured into structured, self-reinforcing networks capable of progressive complexity. The stage was set for the final gradual steps toward life. Compounds had accumulated in sufficient diversity and complexity. Energy inputs were constant. Chemical networks had become self-sustaining in multiple niches, and feedback mechanisms ensured persistence and propagation. Though still devoid of life, Earth's chemical landscape had achieved a remarkable level of organization. It was a dynamic, interconnected system where molecules interacted in structured yet adaptable ways, poised to transition toward the earliest molecular precursors capable of replication and catalysis. As the first billion years of Earth's history unfolded, the planet remained a landscape of continuous chemical activity. Molecules, polymers, and networks interacted across oceans, pools, and hydrothermal systems, forming connections that were stable yet adaptable. Energy from sunlight, geothermal heat, and occasional lightning sustained these interactions, while mineral surfaces and environmental compartmentalization preserved and guided molecular assemblies. Though life had not yet emerged, the planet had developed a remarkable level of organization, a vast dynamic chemical web operating on scales from microscopic pools to planetary oceans. The diversity of microenvironments fostered the incremental accumulation of complexity. Shallow pools concentrated molecules exposed to photochemical and electrical energy. Deep hydrothermal vents sustained sequential reactions in mineral-rich, thermally stable channels. Compounds migrated between these environments, linking localized networks and reinforcing the global connectivity of prebiotic chemistry. Molecules that persisted contributed to increasingly intricate systems, displaying primitive feedback, interdependence, and resilience, all without the influence of a lunar companion. Geology and chemistry remained inseparable partners in shaping this prebiotic Earth. Rising landforms, volcanic eruptions, shifting crustal plates, and flowing waters continually modified the distribution of molecules, creating transient zones of opportunity where reactions could proceed efficiently. Even sporadic meteorite impacts contributed both material and energy, perturbing systems just enough to prevent stagnation without disrupting the overall progression of complexity. Over time, these processes laid the foundation for the earliest chemical networks capable of self-maintenance and selective persistence. Viewed from a distance, pre-moon Earth might have appeared chaotic, with storms sweeping across young oceans and volcanic plumes rising from nascent continents. Yet beneath this apparent turbulence, a hidden order was emerging. Molecules aligned, reacted, and persisted in interdependent networks, gradually forming structures that foreshadowed the first proto-biological systems. Each interaction, each polymer formed and stabilized, represented a step toward the emergence of life's earliest chemical foundations. The absence of the moon did not hinder this progression. While tidal forces would later modulate oceans and influence biological rhythms, early Earth relied on rotation, axial tilt variations, geothermal gradients, and environmental heterogeneity to drive the necessary movement and energy flux. These factors, combined with persistent chemical networks, provided the essential scaffolding for complexity to accumulate steadily over millions of years. As night fell across this young planet, surface waters cooled and wind patterns shifted, yet the chemical networks persisted. Hydrothermal vents continued to channel energy and catalyze reactions deep beneath the surface. Shallow pools, refreshed by rainfall and exposed to the first glimmers of starlight, concentrated and recombined molecules in cyclical patterns. Across the planet, prebiotic chemistry operated with remarkable coherence, quietly orchestrating the assembly of increasingly sophisticated molecular systems. In reflection, the story of Earth before the moon is not one of emptiness or inactivity, but of relentless, patient chemical evolution. Molecules moved, reacted, stabilized, and organized in ways that set the stage for life. Energy, minerals, water, and chemistry combined to create a planet capable of sustaining complexity. even in the absence of a lunar companion. This period was a time of preparation, a quiet prelude in which Earth's chemical canvas was gradually painted with the intricate patterns that would one day support living systems. And so, as we imagine the planet's ancient oceans, hydrothermal channels, and shallow pools, we can appreciate the profound subtlety of prebiotic evolution. Each molecule played a role. Each reaction contributed to an emerging order, and the cumulative effect of countless interactions over millions of years produced a world ready for life. In this silence before the moon, Earth was alive with potential, its chemical networks humming with activity, preparing patiently for the eventual spark that would transform chemistry into biology.